Well, good morning. Thanks for having me here. It's my first time to Russia, and I'm very happy to have come here. The keynote is titled Machine Learning, Offense, and the Future of Automation. And I'll just get started. So the first big thing to say is it is a keynote, which means it is not a scientific talk. Scientific talks tend to be, or at least should have, facts and verifiable things. Given that it's a keynote, it's mostly opinions. It's what I think. Now, unfortunately, I often think things that are quite wrong, so be prepared to disagree, and I also expect to be wrong about quite a few of the things I'll be talking about in this talk. All right, so it is 2017, and everybody talks about machine learning or AI, and are we at the peak of the hype of AI? Because everybody's talking about it, and according to Gartner, we are at the peak hype, because they published this curve, and can't see the laser, but they published this curve, and at the moment, deep learning, machine learning is at the height of the cycle, and it's really only going to go downhill from here. But interestingly, it may be possible that I have gotten caught up in that hype, because for all of the 2000s, I used to make fun of everything that had to do with machine learning, because every time somebody said machine learning, I pretty much heard, oh, I'm going to use, collect a bunch of irrelevant data, and then run some algorithm I don't understand on it, and then make some claims. Because I had seen too many people try to do machine learning and then come up with some crazy way to look whether a PE file is packed and not realizing that that's what they're doing. So I started digging a little bit into the mathematics of it in the early 2010, and I was surprised that below all the hype and below all the idiocy, there was actually a lot of really good computer science and a lot of really good mathematics below it. And in a way, I became converted, perhaps not converted. The point is that I've always believed in good computer science, and if you call the good computer science machine learning now, then I'm willing to believe in that as well. So, what will this talk be about? One of the important points of this talk is not all of that AI hype is bullshit. There's actual real progress. There's some algorithmic changes that came in the last 20, 30 years that bring you order of magnitude speed-ups, like going from n squared to ON, or going from ON to O log n, and that's a big change. And then the second thing is that heterogeneous computing, faster GPUs and so forth, shift the boundary of what is possible just by having more compute. Another key point of the talk is AI is much less magic than you think. It's really college-level applied mathematics, nothing too fancy. It's derivatives mostly, and lots of computational power. And the larger point I want to make is that the biggest potential for all of this is for problems which don't change over time, meaning problems where the things that you're going to train on resemble the problems in the real world. And interestingly, most offensive problems are kind of stable in time. Interestingly, though, on the defensive side, while many problems are stable in time, the problems that the defensive community is focusing on seem to be not stable. All right, so the topics that we'll cover in this talk is, first I'll go on a fairly long bender about what are the key algorithmic drivers that actually make this entire ML and AI hype possible. What are the advances? And then I'll talk about why most of the defensive applications of machine learning are wrong, and why the most promising area may be offensive applications. And then I'll talk a little bit about where are people already using ML offensively, sometimes without realizing, and what are the promising areas where I think progress can be made and will be made. Short caveat, when I say defensive applications are wrong, I don't mean don't do them, or they can never be made to work for a while. Just saying that they're not ideally suited for machine learning. All right, so what are the algorithmic drivers behind the ML hype? What's pushing things forward? And there's essentially three algorithmic bits of it, or at least as I view it, there's three algorithmic bits. There's something called automated differentiation, invented in 1976, and reinvented several times thereafter. There's something called locality-sensitive hashing, invented in 98 and 99 at Alta Vista and Google, and then formalized in 2003. And finally, there's something called Monte Carlo tree search, essentially invented in 2006. And these are really pushing a lot of the advances that we see. There's a whole bunch of other drivers, engineering-wise, meaning people have gotten better at building neural networks. They've got much larger data sets to train from. We've got much better hardware to train these things, and we've been a little bit more clever in what sort of activation functions we use. But I won't discuss the engineering drivers too much. I will focus on the algorithmic and computer science drivers. Okay, so automated differentiation is really one of the big drivers, and it's a bit surprising that it is so important now, because it was invented quite early in the 70s by a Finnish guy called Seppo Linnainmaa, I think, while walking in a park in Helsinki. And it has been reinvented many times over in different communities. It's also known as the Bauer-Strassen method, or as a joint mode differentiation, and so forth. And the neural network, people call it backpropagation. And what does it give you? It gives you as a key result something called the cheap gradient principle. What is the cheap gradient principle? So when you have a function from a high-dimensional vector space to a single vector, to a single number, like from R to N to R, people think that intuitively that in order to calculate the derivative of it, you need to evaluate it n times, because your intuitive way you're being taught derivatives in high school means you do the difference of, well, the quotient of differences. So people think you have an order of n times evaluating the function in order to calculate the derivative. And automated differentiation gives you the derivative, or the gradient even, of the function at roughly the same cost as evaluating the function. So there's a fairly big constant overhead of about less than 30. But aside from that, the order of magnitude for calculating the gradient is the same as evaluating. And that's pretty interesting, because it means that if you can calculate a function, you can calculate the gradient for it as well. And that's surprising, because it moves a lot of problems that look to be quadratic otherwise to be linear. And that also means that you can train statistical models with millions of variables, because, well, calculating the model is easy, then calculating the gradient is also easy. And we can now train neural networks with millions of variables. So I tried to make a really intuitive slide about automatic differentiation, and then I gave up. So my math professor in university said there's only 2 levels of difficulty in mathematics. There's trivial and not understood. The fact that I failed at making an intuitive slide means that I haven't fully understood it. The point essentially is you calculate your function forward, and the function is composed out of many small operations. And you know the analytic derivative for every component. Like you can derive sinus, you can derive plus, you can derive the multiplication. And you evaluate it forward once, and you keep track of all your intermediate values. And then you have a backward sweep where you can collect all of these things and then return, well, get the gradient out of it. I will not pretend that I can explain this better at the moment, so I'll skip this slide. The most important thing for this, though, is that it means you can literally differentiate your code. Meaning there's, for example, a C++ library called fatbad. We can write a function in C++, or a lambda in C++, that does calculations on a bunch of floats. And you can then ask the library, now, please give me the derivative of my C++ code. Please give me the gradient through my C++ code. And that's pretty awesome. And if you look at something like TensorFlow or Torch or whatever, they all want you to create these computational graphs, which are essentially just domain-specific languages for specifying a function. And then they will do exactly this algorithm to give you the gradients and to do optimization on them. And there's TensorFlow for writing these neural networks. There's fatbad if you need to differentiate C++ code. And there's autograd, which allows you to differentiate your Python NumPy functions. And the first time I understood that essentially you can take a piece of code, like an actual computer function, not a mathematical function, and ask an algorithm, can you please give me the derivative of this? I was quite impressed. Anyhow, so automated differentiation, one of the key drivers of all of the machine learning stuff. The second big driver of a lot of the things that we're seeing now is called locality-sensitive hashing. And amusingly, it was invented at Alta Vista once by a guy called Broder, and then it was reinvented at Google a year later by a guy called Charikar. And then after they had both published their concrete versions of it, a professor at MIT called Indig formalized it all and extended it to other problems. And they all won the 2012 ACM Theory and Practice Award for it. And that's unsurprising, because it gives you something quite valuable. It gives you cheap approximate nearest neighbors in high dimensions. Meaning, if I have a whole bunch of data points in a high dimensional space, and I have a single data point, I can now ask, hey, can you give me everything that's close to this data point in the large set of other things? So old solutions, like prior to 2002, 2003, when I was still in university, the common wisdom was that you need O of the order of n instructions in order to find the nearest neighbors, where n is the size of your index, which is really bad if you think about it, because a simple tree, like a B tree, for searching the concrete value is logarithmic. So you can't really afford to do high-dimensional nearest neighbor searches. And by the way, when I wrote BinDiff, because I didn't know about these results, BinDiff did many things wrong in retrospect that I would do differently now. And the beauty of locality-sensitive hashing is that it gives you similarity search in high dimensions logarithmically in the size of the index, which means out of a sudden I can search in billions of items for something that looks similar to the thing I've got. And that's a big game changer because, well, whenever you can put a log in front of your number, it tends to get smaller. Okay, what's the basic idea? So locality-sensitive hashing can actually be explained easily. The basic idea is you need to generate a family of hash functions. So you've got your input data, and you need to build a few hundred hashes, and they all have to have the property that if 2 points are close together, closer than, for example, the distance r, then the probability of them hashing to the same value needs to be bigger than p1. If the 2 points are further apart than distance r, then the probability needs to be smaller than p1. So in essence, the intuitive way to look at it is similar elements have a higher probability of having the same hash function or the same hash output, and dissimilar elements have a low probability of having the same hash output. And that's really all there is. And as soon as you can construct a hash family like this, you can solve the similarity search problem easily. Let's do a concrete example. There's an open source library called Annoy. And Annoy is one of my favorite libraries because it was written by a guy that worked for Spotify at the time during a hack week. And he just wrote it without any theoretical background and just because he thought it's a good idea. And when he just wrote it in 1 week, it started outperforming the best academic state of the art. So it's a fun little library. And it is used for doing similarity search over high-dimensional real vector spaces. So you have a bunch of points in high-dimensional R. And the trick it applies is it takes 2 random points, and then it samples a 3rd point. And it checks, is my new point closer to my point A or closer to my point B, the first 2 points you choose. And if it is closer to A, as in this case, then it'll just average the point with A and create a new synthetic point. And then it'll repeat the same thing. It'll draw the next item, see, is it closer to my new point or is it closer to B? And then average them together again and iterate. And it does this over time. And by this, it chooses 2 synthetic points in space. And then it splits the space in between those 2 points. And then it recurses on both sides of the split. And what you get from this is you get a sort of irregular, kind of random tiling of the space into many little pieces. And you can look up very easily, hey, is this point here, in which tile does this fall? Because you just have to say, is it left or right of my line? Is it left or right of the other line? And so forth. So you search through this, and you end up in one particular area of space. And all the points in that area have been put into the same bucket. And now you can do this n times. So it's very easy to search for the right tile that a dot is in. And then you can create many such tilings. So you have your space, you cut it into pieces 1 time, build a tree. You have your space, you cut it into pieces a different way, and again, and again, and again. And these trees are your hash function for r to the power of n, because, as you can see here, points that are close together have a higher probability of being in the same bucket than points that are far apart. And it's a surprisingly simple algorithm, and it's surprisingly effective, in the sense that Annoy runs on a single core and it's a single machine. And it's quite easy to have 40 million, 50 million data points and do effective queries into these data points, even though they may have a dimension of a few thousand. So that's a very, very powerful library and generally a clever idea that I'm envious of. All right, the third driver of what we call AI at the moment is something called Monte Carlo tree search. And Monte Carlo tree search was invented in the context of Go playing. So before 2006, the conventional wisdom was that most Go programs can be beaten by anybody with half a brain. And starting in 2006, they started to become much stronger very quickly, so that most amateurs couldn't beat them anymore. And a lot of that improvement is due to clever improvements in Monte Carlo tree search. And the idea behind it is a generalization of something called upper confidence bounds applied to trees. I'll go into that in a bit. It's essentially a way that when you have a large search space and a large tree that you need to explore, to balance exploring the tree, like trying out random things, and going to the place where the tree looks most promising. So it essentially helps you guide your way through a very large search space that you don't understand otherwise. And the idea starts with something called the multi-arm bandit problem. The multi-arm bandit problem, imagine you have slot machines. You're in Las Vegas, you have slot machines, 3 of them, or many of them, and they have different payout schedules, meaning they pay you a different number in expectation. And you don't know that number, you just know that the payout stays fixed over time. So what's the best way of choosing which slot machine to play in what order? And the idea is that assuming that you already have some measurements for the different slot machines, because you've played randomly a few times, you have expectation values for your payout that you've measured. So you have an estimate for what the payout of the machine is, and because you have different numbers of samples for every machine, you have different levels of uncertainty around them, meaning if you have few numbers for a machine, you're more uncertain about your estimate, whereas if you have many numbers for a machine, you're quite certain about the estimate. So you have an interval of uncertainty around your payout, and the algorithm is essentially be optimistic in face of uncertainty, meaning always play with a thing, like with the slot machine, that has the highest payout when you factor in your uncertainty. So in this example, the thing on the right has the highest payout when you factor in the uncertainty. So you play that one, and by playing that slot machine, you shrink your uncertainty because you collect data about it, and you slightly grow the uncertainty of the other slot machines. So what this helps you do is essentially always play with a thing that has the highest promise for paying out more money, and then you still will explore all other possibilities depending on over the period of your game, but you will at the same time maximize your payout. And the idea behind the tree search is you do the same, but for game trees. So you have a game tree for multiple moves through an iterative game, and you start out by selecting the one where your level of uncertainty and the experience from playing that thing is the best. So in this case, we have a node where we know that we won 3 out of 3 games that we played. So we choose that node, and we choose a random new move from that node forward, and then we randomly play the game to the end and see whether we win or lose. And in this case, we lose. So we update the probabilities for all of these nodes up on the tree, and you just iterate this over and over again. And it's a really, really interesting algorithm that, by the way, is now used for a lot of computer game AIs, because it essentially gets stronger the more time you give it. So you can calibrate the strength of your opponent by just giving it less time to compute, and over time it'll approximate the best game it could have played over time. Anyhow, so Monte Carlo tree search. And we've now been through these 3 examples, like through cheap differentiation, through locality-sensitive hashing, and through Monte Carlo tree search. And it's really interesting to look at all the big advances that have hit the press and have been discussed in AI. They're almost always combinations of these 3 things. So an image similarity search, for example, is cheap gradients and locality-sensitive hashing. So you have a neural network that extracts a vector, and then you do locality-sensitive hashing to find a similar vector. AlphaGo 0 is cheap gradients and Monte Carlo tree search. So they have a neural network to estimate the value of a position in Go, and then they play Monte Carlo tree search in order to actually choose moves. So it's quite interesting to see how you can just mix and match these different technologies, and they always seem to generate interesting combinations and interesting results. Anyhow, enough of mathematics for the moment. Let's talk a little bit more about why are most defensive applications of machine learning and security wrong, or at least not the ideal place to apply machine learning. Apologies for all the mathematics, by the way. I see people in the audience be a little bit tired. Okay, so what does machine learning do? Machine learning estimates a probability distribution from a bunch of samples. So the golden rule of all machine learning needs to be the thing you need to work on needs to resemble the thing you trained on. That's the only important rule that you need to respect in a way. Like training to speak French does not help me speak Russian. So unfortunately, we seem to neglect this quite often. Many people think of IT security as like a conflict between the attackers and the defenders, like a direct conflict. But this is not actually the way that IT security is set up. If you think about it a little bit more, the reality is more like you have an attacker, you have a defender, and you've got the world, where the world means the legitimate users of an enterprise, everybody that tries to just do their work, that isn't involved in security themselves. And then people think that the conflict is between attacker and defender, but most of the work the attacker does is actually not aimed at the defender. Almost all the work that the attacker does is aimed at the world. So the attacker has to phish users or deceive users. He has to traverse the target's network. He has to find bugs in software that the world has written. He has to write exploits for those bugs. He has to persist in the networks of the world. And likewise, most of the work of the defender is also against the world, in the sense that he has to educate the world, he has to make the network more easily defensible, he has to provide safe defaults for the world to use, tell them how to properly program without error. He has to do authentication and access control and so forth. And it's really only a sideshow. It's only a very minor part of the job of the defender to detect the attacker. It's only a very minor part of the job of the attacker to evade detection. So most of the games you play in security are not games played between attacker and defender. Most of the games are played between either attacker against the world or defender against the world. And the important thing about the world is the world does not change to screw you over. Meaning the world does what it does, it tries to get its work done, the developers develop their software, the people click on their emails and so forth, but they don't try to change their behavior just to screw you over. Because there are billions of people and you're one guy. The only person or the only part of this diagram which does change their behavior all the time adversarially is the attacker. So that means that all the work that we do where either the attacker or the defender works against the world means that the problem distribution is stable in time because the world doesn't change. And the only place where the distribution isn't stable is on the left-hand side of the diagram, which is detection and evasion. So you can argue that the worst place to apply machine learning, if you think about it, is in detection. Because that's the only place where stuff will change all the time and change maliciously. So it's interesting that the place where we put most effort in using machine learning is also the place that is least suited for it. Okay, so examples of things that are really difficult to make work in the long run. Detecting whether software is malicious. That's going to be super difficult because there's so many degrees of maliciousness and so many ways to define maliciousness. And and the attacker can change the way that he behaves all the time. You can't train malicious, non-malicious reasonably because the attacker will find a different way to be malicious, change the distribution, and you're screwed. The same is malicious behavior of users. You can't reasonably train a machine learning model to detect malicious behavior by users and non-malicious behavior because the attackers will change their behavior and then find a different way to be malicious. Likewise, authentication. All of these are examples where your training data does not resemble the data you have to work on in the real world. Anyhow, enough about defense. Let's talk about offensive uses of ML and AI. Where is it already used and what are promising future areas? And at the moment, offense is a bit of a cottage industry. It's a bit strange. You have these people that are doing highly artisanal work. Like they know how to find a bug, they know how to write an exploit, but it's not an industry. It's like you go to a tailor. Like you go to an offensive person, and that offensive person is like a tailor in the sense that he will do whatever he does. And most of the practitioners in offensive work have very limited tooling. They get by persistence, by talent, by sheer work. But there's a lot of unpredictability in development, and there's not a lot of tooling. Interestingly, the offensive community is generally quite averse to adapting new tools, or even to maintain tools over time to keep them going. On the other hand, there are a few tools that the offensive community has adapted, and perhaps they've adapted them without knowing that they're doing machine learning somewhere. Now, one crucial thing to say about artificial intelligence is a lot of artificial intelligence is really just brute force. Like people underestimate the sheer effectiveness of brute force in solving problems. And there's a smart person that doesn't want to be mentioned that I had this discussion with, and he really hammered home to me, hey, seriously, when you talk about AI, most of it, like it always has a massive, big tree search component. So if you look at Deep Blue, when it beat Kasparov in chess, it had 480 specialized ASICs just for brute force tree search through a chessboard. And AlphaGo, when it beat Lee Sedol, had like 2,000 CPUs and 300 GPUs running. So that's a lot of compute. People don't view brute force as an important component of intelligence, but it is. And now I'm going to make an outrageous claim. My outrageous claim is that AFL is already a superhuman machine learning bug finder. And everybody will be like, what the hell? AFL has nothing to do with machine learning. What are you saying? You're crazy. Now, first of all, AFL already has more CVEs than any individual ever and has found more bugs than any individual ever. And AFL has a lot of really clever things under the hood if you look inside. It does a lot of brute force, but it really cleverly combines this with genetic algorithms to splice examples together. And then it has a very, very carefully balanced exploration-exploitation trade-off where it tries the same sample, like the same input, more often if it gets better feedback from it. And then it has a curiosity bonus where if it sees new behavior, that example will jump to the front of the queue and be fuzzed much more. And if you look at DeepMind and them playing Atari games, they used to fail really badly on a game called Montezuma's Revenge, and only recently had better results by adding curiosity to their machine learning algorithm. So AFL already has something like this in there. And it learns something because you can take the corpus generated from AFL on one PDF parser, and you can use that with benefit on another PDF parser, because it learns from one executable what gives me more coverage, and then you can use it on a different one. And the success of AFL is quite hilarious, because if you look at the Cyber Grand Challenge the Americans ran, almost all of the competitors were very thin layers over AFL. So you had a competition of 10 teams that were all doing different things to tweak their AFL a bit, but AFL was the underlying driver of the engines for all of them. So my suspicion is, well, the title of this slide is a bit of a joke. You have to say it with a heavy French accent. It works in practice, but does it work in theory? I used to think that breakthroughs in computing come from first the theoretical breakthrough, and then you have an innovation coming from the theoretical breakthrough. But my experience over my life has been that real progress is something starts to work and nobody has an idea why. And then the theory gets built in order to understand why the hell is this working. And I suspect we have a similar situation with AFL where it works. We don't quite know why exactly, but we'll figure it out eventually, and that'll help us. So aside from fuzzing in AFL, which is the most obvious example of ML in offensive tasks, ML is really good at recognition. So it's perhaps no wonder that the most papers we've seen on offensive uses of ML are recognition tasks. There's a Wood paper from 2011, which looks at source code patches and then looks locally around that patch and sees whether there's similar places in the code which weren't patched. So let's say you have something like an FFmpeg parser, and they have a bug somewhere, and they patch that bug, then it looks for similar variants of the same thing elsewhere in the code base and highlights them. And that's quite effective. And then there were two papers in 2016 and 2017 which do search for vulnerable assembly in firmware images by essentially having some sort of machine learning front end and then locality sensitive hashing to search into a big database. So firmware, like finding bugs in firmware, because like known bugs in firmware is another area. And it's perhaps unsurprising because ML is really good at recognizing similarity. Where we are starting to see the first progress now is in heap layout. If you think, like if you ever write a heap exploit, trying to figure out the proper sequence of inputs to arrange the heap correctly in order to do something is very much like a board game if you think about it. You have a limited number of moves and you need to combine these moves cleverly to get a particular layout. So I think that we'll see a lot of progress there. And the first thing that is getting published now in a month or so at Black Hat Europe is something called Black Box Randomized Tree Search for heap layout, which is still relatively simple. They essentially search by trying a lot of different interactions for a heap layout that is beneficial for them. But as I said, brute force is a big component of intelligence, so this is progress. So where will we see more of this stuff? Where do we see interesting results in security from machine learning? Pretty much anywhere where we have a stable distribution of the problem, which means bug detection, because programmers do not change quickly, Exploitation, because my target does not change very quickly. The bug I have in Firefox today is a bug I have, and the bug I have in Firefox in 3 months will require very similar steps in order to do the exploitation. Firefox changes, but not so quickly. Phishing and user deception, that's probably the classical one, because most of this ML stuff was developed in order to get people to click on things. It's very, very clear that writing a good phishing email is a classical ML problem. Autonomous lateral movement. Most Windows-centric organizations have a very similar network structure, so learning to hack one of them is probably going to help you hack the next one. And then, of course, password cracking, where you have lots and lots of data, and some password combinations are just much more likely than others. So it makes sense when you try cracking passwords to start with things that are similar to what people use first. On the bug detection front, I think we'll get, or I hope we'll get, much better automated analysis of source code and binary updates, meaning when patches are shipped, you have something that looks at these patches and tells you this is interesting for security, this is not interesting for security, and these are really interesting for security. And also trying to backport things to old versions. So you see perhaps a patch in the Linux kernel, and it can see whether it's security relevant and then tells you which kernels in the past were affected by this. Another thing that I would like to see being done, but it's much harder, is inferring the intent of a piece of code. When I try to look for vulnerabilities, I often look at a function and ask myself, does the function do what the programmer thinks it does, or what the programmer wants it to do? And it's very, very difficult to reason about this automatically, because inferring what the programmer wants it to do is very difficult. So perhaps as we get better at inferring intent, we'll be able to actually look at code and see, hey, is this doing what the programmer wants it to do? And then, of course, we'll get a lot of good tooling for finding cut and paste vulnerabilities and repetitions of the same thing. So variant detection of bugs is something that is going to be changed quite drastically. We'll get better fuzzing. As we understand what AFL does better, we'll understand better what's the exploration-exploitation trade-off, and we'll get neural networks or whatever else to generate input corpora for us. There's a new type of neural network that has emerged in the last 1.5 years called GANs, Generative Adversarial Networks, and they've gotten really good at faking complicated input data, and I think they'll be quite good at generating plausible-looking files that you can throw into a parser. So you feed them a bunch of PDFs, and they'll generate a new PDF for you, combining different features from the PDFs. Exploitation. Now, exploitation is something that is very close to my heart as a practice. I'm looking forward to the stuff that people will do there. I think people will have automated exploration of heap layouts after a fuzz crash. They do this by hand already now. Like when you fuzz something, you usually try to crash it a few more times to see what changes on the heap and which of the crashes looks best for you. Then learning how to manipulate the heap layouts for a given target, because most people that work in offense target the same software over and over again. So somebody does Chrome, he does Chrome, he does Chrome, he does Chrome. So automating the heap layout for a particular target makes a lot of sense. And then I'm hoping that eventually we'll get to a point where we can have some automatic discovery of exploit primitives. Because when you exploit something these days, you often have to combine multiple primitives. Or I can get an information leak from this, I can get a write for with some restrictions from this, and so forth. And just trying out a few billion cases to see what are the different primitives I can obtain would make the construction of the exploit much easier for the exploit developer. Because he would no longer be faced with, oh, you've got to try this, 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 and this, and then make something out of it. But you would be given options. Hey, you've got this, you've got this, you've got this. Now try to build something from it. I'm also hoping that once this gets going, we'll see a bit of a timescale compression. Because right now, when you diff a patch and you find a vulnerability, it still takes a fair bit of time to turn that into an exploit. And it would be really nice to push that down again to like a day or two. That would be more fun. Okay, then phishing and user deception, of course, that'll be a big thing. If you think about why is Facebook, why is Google interested in machine learning in the first place, they were interested because they used to use it a lot for advertisement placement and getting people to click through. So you can say that getting people to click on things, that's the one thing that we know machine learning is fantastic at. Anyhow, now after I've spoken about offensive uses of ML, what are interesting and perhaps not so prevalent defensive uses of ML? Where do we have a really stable distribution on the defensive side, and what's perhaps a way that isn't commonly discussed about how to use it there? And one thing which may be really interesting is deception, in the sense that if you look at 1960s espionage, when somebody found a spy in his organization, they would usually start feeding that spy wrong information for a while, because that way the attacker that was receiving the information could no longer know which of the information he got was true, and at which point it started becoming false. Now, I've been in incident response a few times, and I've been in a few situations where I would have loved to be able to just feed bullshit to the attacker for a while, for like give him all the data he wants for a month, but it's all wrong, all false, all garbage. But it doesn't work, because in cyber, in computers, people exfiltrate gigabytes and gigabytes of information, and nobody can generate enough bullshit. And the interesting question, or the interesting thing with machine learning now is they get really good at generating bullshit. So this is an academic result that is only like 4 weeks old. A few guys in Finland managed to build a generative adversarial network that generates celebrity images. Like you train it on a few thousand celebrity images, and it generates a new male and female celebrity face. And these faces look pretty convincing. Unfortunately, the algorithm learned that women's faces have to be photoshopped, because the woman's face doesn't have any pores and the man has greasy skin. But they look very, very convincing, which means that we're getting to a point where stuff like an employee directory for a company could be generated arbitrarily. You could probably generate like 20,000 pictures of people, and they would look like people, and they would be genuinely indiscernible from actual people. And you can train a very simple recurrent neural network on the Linux kernel, and it'll, like on very little, like in one afternoon of work, it'll spit out C code that vaguely looks like Linux kernel code. I mean, it's ugly and it won't compile yet, but just combine it with a compiler, and you'll very quickly get to a point where you can generate a gigabyte of confidential source code that compiles, makes no sense whatsoever. And then, can we generate an entirely fake Windows domain? Can we generate an entirely fake network? I think we can probably generate corporate emails, because corporate emails are already so bullshit-laden that they're hard to distinguish and easy to generate. Can you generate false blueprints? It's an interesting question. I think that there's lots of interesting work to be done on that front. But the question is, will the attacker be able to distinguish, or are we going to make the same mistake we're making with the detection again, where we try to target a maliciously changing distribution? I don't know. Anyhow, so the summary of the talk is not all of this AI hype is bullshit. There's actual good work being done, and algorithmic improvements that are impressive, and heterogeneous computing, GPUs, FPGAs, ASICs make a big difference. AI and ML is much less magic than you think. And the biggest potential is stable in time distributions. Most offensive problems seem to be stable in time. Most defensive problems too, but they don't seem to be the focus of machine learning efforts. So perhaps it's going to be time to focus more on the stable problems. And that's the end of my talk, and enjoy the rest of the conference.